interference phenomena occur when two or more waves superimpose each other to form a new resultant wave under certain conditions. And the resultant waves are governed by the superposition principle.
Oh, I know about that. When two or more waves overlap each other, the resultant disturbance is the sum of individual disturbances.
Exactly.
By the way, teacher, what are the criteria for waves to form interference?
Let's discuss it. First and foremost, two waves must have the same wavelength. For instance, if the waves are light,
they should be monochromatic.
Exactly. Next, the source waves must be coherent, which means they must emit waves with constant phase difference.
Coherent source? Never heard of that before. And why must the sources be coherent for interference to happen?
Well, this can be understood by the concept of phase difference. Let me show you. Let's consider 2-point sources, say S1 and S2, whose waves meet at point P traveling different paths x1 and x2 respectively. Here, the phase difference between the waves meeting at point P depends on the paths they are following, for example, x1 and x2, and also on the frequency of the sources, S1 and S2. In fact, the phase difference at point P is the sum of the phase difference due to a difference in frequency of the two sources, and the phase difference that arises due to the path difference of x1 and x2. Since the frequencies of the different sources are different, that means the phase difference encountered at P changes with time. In other words, no constant phase difference is achieved at point P. In order to achieve a constant phase difference, the sources should be maintained in such a way that the phase difference at point P becomes independent of time. That's possible only if the frequency of sources S1 and S2 are the same. Thus, coherent sources are the sources that have both the same frequency as well as constant phase difference.
Oh, I understand now. Two waves sources are coherent only if they maintain a constant phase difference. And constant phase differences can only be achieved if frequency of these waves are the same.
Finding this helpful? We have additional learning resources to offer. For Cambridge IGCSE and AS A-level subjects.
Is it possible for independent sources to have the same wavelength and constant phase difference?
Well, even though you can have two independent sources with the same wavelength, they will never maintain a constant phase difference.
I guess it's not possible then.
Actually, there's a way around it. We take a monochromatic source of a wave, for instance, and pass it from two small nearby slits. Then, the wave in each slit acts as a new source with the same frequency and constant phase difference because they are basically from the same parent source.
Oh wow, that's a great idea! Now these two sources fulfill the conditions for interference.
Absolutely. The sources are now coherent. This is exactly how we obtained two coherent sources while performing interference experiments.
Wow, that's ingenious. So what about sound waves? How do we make them coherent?
It's pretty simple as well. For that, we can use two speakers and connect them to the same signal generator.
Ooh, that's really cool.
It is. We can perform interference experiments using water waves and microwaves too.
Whoa. So, teacher, what will happen when these two coherent waves superimpose?
Simply put, two things may happen. They either interfere constructively or destructively.
Uh-huh.
Let's start with constructive interference first. This occurs when the crest of one wave combines with the crest of another wave, and the trough of one combines with the trough of another to form a resultant wave. And the amplitude of the resultant wave is the sum of amplitude of individual waves.
Oh, so if both waves have the amplitude of A, then the amplitude of the resultant wave must be 2A, right?
Exactly. And as a result of this, the intensity becomes maximum during constructive interference. Moving on, what about the path difference of two waves for constructive interference?
Since you've mentioned a wave's crest is superimposed over another's crest and the trough over the other trough, there is zero path difference between the waves.
That's partially true. Constructive interference still can be obtained if there's a path difference between two waves equal to 1 lambda, 2 lambda, and so on. Thus, for constructive interference, the path difference should be the integral multiple of lambda.
I see. So in terms of phase difference, constructive interference occurs only when waves are in phase with each other. In other words, the phase difference are 0, 2 pi, 4 pi, and so on, right?
Bingo! Pretty simple to understand, right?
Yep.
Alrighty. So, let's move on to destructive interference.
I know. Is it one wave cancelling out the other wave?
Absolutely. When a crest of one wave combines with the trough of another, or vice versa, they cancel each other out. This type of interaction is known as destructive interference.
Got it. And when these two waves with the same amplitude interfere destructively, the resultant amplitude is 0, right?
Yep. Zero amplitude means zero intensity, which means the region is dark for light waves and quiet if sound waves are used.
I see. That's really straightforward.
And just like before, what do you think of the path difference for destructive interference?
Since destructive interference means a wave's crest superimposes over another's trough, isn't their path difference half the wavelength or half lambda?
Correct. But remember, just like constructive interference, destructive interference also repeats after every complete wavelength.
In that case, the other path differences for destructive interference are half lambda, 3 lambda over 2, 5 lambda over 2, and so on.
Go on.
Thus, the corresponding phase differences are pi, 3 pi, 5 pi, and so on. And the condition is out of phase.
Register now for free.